All right, ladies and gentlemen, today I'm going to be talking about the ratio test. Okay, this is another test for series. There's about 9 tests in total. This year we don't have to cover every single one of them, but one of them that we do have to cover is the ratio test. Okay, so now the ratio test, before I go over what it is typically used in series that contain factorials. If you remember, a factorial, like n factorial, is n times n minus 1 times n minus 2 times n minus 3, all the way down to 3 times 2 times 1. It's just that repeated multiplication of one integer less and less and less, right? And why do we use this in a ratio test? Because when you set up a ratio of factorials, a lot of those factors are going to end up canceling out. So, for example, if you had n plus 1 factorial over n factorial, if we write it out, you can see the n's would cancel, the n minus 1s, n minus 2s, n minus 3s, everything in the middle, 3, 2, 1, all of that stuff is going to cancel out, leaving you with just n plus 1, okay? And when we talk about ratios in the ratio test, a lot of times you'll see we use this with factorials, but there are some other times, and I may do an example where we actually do a ratio test on something that does not have factorials, but we do use it a lot with factorials, okay? So what does the ratio test say? The ratio test says, let's say you're given a series where a sub n is the general term. It's from n equals 0 to infinity. If we take a limit of the n plus 1 term, the n plus 1 term, over the nth term, and we get some value L. We get anything. It doesn't have to be like a specific value, but if L is less than 1, we're going to say it converges. If L is greater than 1, it diverges. And if L is equal to 1, the test is inconclusive, and we have to use something else to determine whether or not it converges or diverges. Okay, so now what is this test actually saying? Like why? Why does it work? Well, really, this test is basically saying that as you go out further and further and further terms, as you approach infinity, it really doesn't matter what happens in the first 5 terms or 10 terms or 100 terms. Really what happens is as you go further and further and further out, if we compare 2 terms in a row, way out at the end of the series, or towards infinity, if you compare the 2 of them and you get this ratio, well, where we use the term ratio is with geometric series, right? So L basically acts like a common ratio as you go out many terms. It's saying, does this series start to behave like a geometric series? Does it start to appear that there is a common ratio between 2 successive terms? Does it act geometric as you approach infinity? Well, what do we know about geometric series is that if the common ratio is less than 1, it's going to converge. If it's greater than 1, if the common ratio is greater than 1, it's going to diverge. And if it equals 1, well, we don't know. This test doesn't work or anything like that. But this really just comes from rules for geometric series. Okay, so that's why it is. I mean, we're basically, this ratio test is, does the series eventually look geometric and act geometric? Is there a common ratio, and is that common ratio less than 1? Okay, so let's do a quick example here. We're going to try and do a couple examples. So first example, let's say we have a series starting at n equals 2, going to infinity, and this series is going to be n squared over n minus 1 factorial. Okay, now because it has a factorial in it, we're going to think, let's try the ratio test. Okay, now this ratio test here is basically, we're going to take the limit, sorry, that's my dog, as n goes to infinity of the n plus 1 term over the nth term. Alright, so how do we do that? We just plug in n plus 1 into the general term. Alright, and it's going to look like n plus 1 squared over n plus 1 minus 1 factorial divided by n squared over n minus 1 factorial. So now this is a complex fraction, and for this we're going to multiply by the reciprocal of the denominator, bring it up to the top. So instead it's going to be n plus 1 squared over, that's just going to be n factorial times, now we're going to have n minus 1 factorial all over n squared, right? And so we're going to be taking the limit of that. I'm going to rearrange the factors so that the factorials are on top of each other and the polynomial factors are on top of each other. So that n goes to infinity, we're going to have n minus 1 factorial over n factorial, and we're going to have that n plus 1 squared over n squared. Now, alright, the n minus 1 factorial over n factorial, n minus 1 factorial over n factorial. Well, n factorial is n times n minus 1 times n minus 2, and so on, 3 times 2 times 1. And the numerator is going to be n minus 1 times n minus 2 all the way down to 3 times 2 times 1. Obviously, with everything that crosses out here, the n minus 1s, everything disappearing, this is just going to be equal to 1 over n. So we get a limit as n goes to infinity of n plus 1, squared, all over, now this is going to be 1 over n times n squared, so this is n cubed. This is going to be equal to 0. Well, since 0 is less than 1, we can say the series converges. More importantly, we can say the series converges absolutely, with those absolute values in them as well, okay? And absolute convergence is something that we would pay attention to in previous years. This year's not a big deal to say it, but yes, with the absolute values, we can apply this ratio test to series that have negative terms in it, and essentially it doesn't matter whether the terms are negative or the terms are positive. If this test works and it says it converges, we say it converges absolutely. Okay, let's take a look at another example here. Okay, so this time we're going to have a series n equals 0 to infinity, and this is going to be n factorial all over 5 to the n. Okay. Again, you got your factorial in there. We're going to head and do a ratio test. The limit as n goes to infinity. Now, we're going to just plug in the n plus 1 term, which would be n plus 1 factorial over 5 to the n plus 1 all over n factorial over 5 to the n. Okay, so that's the ratio of the n plus first term over the nth term. We're going to go ahead and multiply by the reciprocal, and I'm going to rearrange some terms so that we have our n plus 1 factorial. That, when we multiply by the reciprocal, is going to end up over the nth factorial times 5 to the n will be in the numerator, and 5 to the n plus 1 will be in the denominator there, okay? And so we can reduce a little bit. You can go through and check my reduction, but this n plus 1 factorial over nth factorial, this is just going to end up being n plus 1 in the numerator. And then over here, the 5 to the n's are going to cancel out, and you're just going to end up with a 5 in the denominator. And so this is going to shoot out to infinity when you take the limit, which means the series diverges. Ooh, diverges. All right, good. So that is the ratio test. I'm going to do one example where the series does not have a factorial in it, but we can still kind of apply this one here. Let's say we have the series as n equals 1 to infinity, and this is going to be negative 10 to the nth all over 4 to the 2n plus 1 times n plus 1. All right, and I'm going to apply the ratio test to this. It looks like it could be geometric or very close to a geometric. There might be ways to use comparison tests. If we learn those things, we don't have to worry about them this year. But we're going to try the ratio test here. So n goes to infinity. All right, now the numerator is going to be negative 10 to the n plus 1 all over 4 to the second times n plus 1 plus 1 times n plus 1 plus 1 all over. So that's the n plus 1 term, and it's just over the nth term. Negative 10 to the n all over 4 to the 2n plus 1 times n plus 1. Now, this is going to reduce, multiply by the reciprocal and so on. You can verify this on your own, but essentially I'm going to get, after a while, right, multiplying by the reciprocal, canceling out common things, I'm going to get negative 10 to the n plus 1 all over negative 10 to the n, right, times 4 to the 2n plus 1 over 4 to the 2n plus 3. And then we're going to have n plus 1 over n plus 2. So you can verify after flipping, multiplying, kind of rearranging that a little bit, that is what you're going to get. And then each term here, the first one is just going to be negative 10. This one here is going to turn out to be 1 over 4 squared. And this stays as n plus 1 over n plus 2. We're taking the limit as n goes to infinity. And this is just going to be 1, right? Because it's a polynomial over a polynomial. You use leading coefficients. We're going to end up with negative 10 over 16, but absolute valued, so that's a positive 10 over 16. That happens to be less than 1. So the series here converges. Absolutely. Okay, and there you have it. That is the ratio test. Do we care what it converges to? Or we not really. I mean, we could go out and try and add up a whole bunch of things and see what it comes close to and try and predict what it would converge to. But we don't really need to do that. We're just asking, does it converge? You know, is it going to slowly get closer to something? And yeah, this ratio test tells me that eventually the terms are going to act like a geometric series with a common ratio of 10 over 16. Doesn't matter that in the first maybe 20 terms it doesn't look that way, but as you move further and further and further out, it behaves geometric with a common ratio of 10 over 16, meaning it will therefore converge, right? And that ends this recording on the ratio test. Thank you.